send me your notes for your first test too, so that side by side two of them. So that's one of the best ways that I've always done is if you have like equation numbers, you'd be like, oh, it's this equation that would. I don't know if I saw use the notes. That's what I mean the notes, so I can pull from slide to slide. I'll do that now.
Let me get this link. How do you find the invite link for it?
Which chapters were covered on the first exam? Which chapters? What?
I think if you start your own meeting, you should be able to
Oh, okay.
record the
Yeah, you
meeting.
can record it soon.
Josh, do you have Gmail on your phone?
Yes, it is.
Okay, I'm gonna email you the link.
And then you should be able to post a link in the group chat that allows people to see
Are you just testing to make sure that I can hear
I think
Yeah.
once you just send it out.
it? I mean, that's fine too. Like,
It was everything from the way electromagnetic through Gauss's law.
Gauss's law, okay. And
His
I'll-
capacitor
I'll
started
download this real quick.
Let's do tomorrow?
4 to 4:30 for setting up this meeting because I'm glad we're doing this now.
That's why I was like, we could start sometime around now. It's just when we get everything going, we can get
Do it in
going.
your class then. Okay.
Okay, so you said Wagon lecture notes. All right, so I'll pull those up.
Yeah, everything up to the first sample exam.
What's up? Was my email?
No, I sent.
I got it. So I will throw that in the group chat. Wow. Well, I mean, I can actually just open it up to see. Let me test real quick. It says that I'm in the waiting room. So let me log in and then make sure that it's working, and then we'll go from there.
I have to confirm everyone is in. Admin. How do I make it so that I don't need to admit people in here? Security.
So that answers got sound. So
No, disable waiting. Okay.
yeah, and you can see him.
How's it centered on the board?
I would say move the camera a little bit to your right. A little bit more. You go. Yeah, you got it. The whole the whole board is not in view.
Oh,
Back it up.
is that a whole?
There you go.
Yeah, perfect. That's perfect right there. All right, well, I'm gonna log off to this and I'll just send the. So it's echoing. Meeting is set up.
I hate the fact that it has things in terms of actual like numbers and answers, so I have to actually do calculations.
To make sure that it's right.
What is, I guess epsilon naught's 99, right?
Yeah.
Do
You want
you have a better calculator?
84 plus CD.
That's good. I don't know what it
I
is.
got the expensive ass test calculator that he's really pushing us.
Yeah,
to
he like.
I will. Can you mind if I use that for like, because I can get equation answers for all these pretty quickly.
So you said electric field. So it's his notes, electric field, electric Gauss's law, and that's it. Oh,
I believe so. Yeah, we
All right.
pushing for us to do it.
It's a pay to win scan. Okay.
Yeah,
The first generation of those calculators are really popular for Game Boy emulation.
yeah.
Yeah.
yeah, because I know when I was in high school, I had a buddy of mine who was able to get Doom on his TI-84.
Yeah.
And I was like, oh my gosh.
Yeah, the things like it runs on Linux based operating system.
So that's why it's just equal. How do they do that though?
Oh, no.
Just say it's just a Linux computer.
But you could, the second generation of the calculator, they put a patch in, so you can't upload certain file types. So you can't upload ISOs onto the anymore.
You just take some work around it.
They've not found a workaround for that calculator. There's a pretty active community behind them. It's really strange.
Everybody's gonna be out of school and they're not using their calculator anymore by the time they come up with the answer.
I watched a LTT video where they overclocked the TI-84. Like they water cooled it and everything.
Have you seen the one where they overclocked like 5 gigs?
Or
It was like, they were like, I think they were like, what is it, NSCEs or something like that, like the
Oh, yeah,
convention. And they overclocked like some Intel processor at 5 gigs.
oh, yeah,
I think I've downloaded all of them. I'm gonna send them to you now.
9th and 10th gen i7s and i5s are great overclocking chips.
So.
But I just got my, I just bought a new Ryzen processor.
Which one?
R7 with the 800X.
Okay,
So that's fine.
my
So go to-
laptop has
sorry, so I sent all the notes to you.
Ryzen 9.
You did?
Yeah,
4900
nice, thank you.
in it.
Which is expensive, so
It wasn't as expensive as you think.
isn't it like $400 though?
No, the laptop.
Oh, the laptop,
Do the laptop, yeah, not the
just the processor itself.
GPUs nowadays, though.
Oh, yeah, oh, yeah.
I mean, people are selling 1080 for fucking.
I wasn't gonna
$1,000.
enforce it because it's kind of only a few people, and
That's-
if
I
I'm
mean,
gonna be
that
speaking for
graphics
3 hours,
card
my
is
voice is gonna have to carry.
2000.
Yeah.
So. I'm just trying to get. I can't do this calculator.
If you can't do these calculations, that's
No,
correct.
it's not-
No, I can do the calculations. I can't do the calculator.
Oh, gotcha.
Yeah, fraction is hidden behind a control. How the fuck is that control?
I'm like, I feel like I'm like literally like trying so hard just to try.
Oh, yeah.
There's a cursor on there too. It has a track.
There's the negative one.
It's over the whole
Yeah, it's at the bottom of your numbers.
They have a track panel.
There's a trackpad on a calculator.
So we're gonna try, what I wanna do is I wanna go over
I think
the
you should make your own
first
program.
exams you guys
time.
had.
Yeah.
I'll do that on the CID.
As best as I can, and then depending on time, which if calculations allow us, we'd like to run through a couple other things as well, but, we're gonna start, I wanna start with number 11 from your exam. I'm trying to get the calculator to work.
If you have like collection.
And it's
Totally not
versus
versus
also
master,
recording, right?
basically.
Yes.
Not really, to be honest.
I still haven't figured out graphing on it.
Oh, yeah, no, I'm not. figured that out.
I haven't figured out graphing and I haven't figured out matrices.
Yeah,
Oh,
you know your
matrices
calculator.
are easy.
I have a matrix.
Does anyone have a less complicated calculator?
I have the,
You know your calculator
like
is
this?
complicated. when you
That's
have to
perfect.
have-
I know how to use this.
They have
I'm gonna
full
check.
courses for those.
Yep, that's right.
But you poor soul.
If you need crosswalk,
That's right, I
I
can
literally
use
have,
this.
like, I looked up and found the program
Got it.
that put it in.
And,
So
and I mean, those,
these have product programs.
I was gonna say, those come in like built with vector calculus
Oh, yeah.
programs and stuff.
for
This
all
thing
you
is
guys,
No, just for that.
Just these ones. Damn, it's paid.
Yeah,
It's
this thing
made away- it's made
it's single-handedly carried me through statistics.
It's scaring me through physics right
It
now.
calculates every distribution known to man.
Oh, wow.
Crazy. I need that.
Oh, Ryan, how was the implementations?
They were done in like 20 minutes.
Really?
Yeah, we got out of there at like 20 after 10.
Really?
I have like 3 classes with you and had no idea you had a beard.
What do you mean? Oh, yeah.
Yeah.
It'd be like that most of the time. When I went to work, I was there the entire time and they stopped, like few last days, they stopped enforcing masks. Everyone was like, you have a beard? I was like, yeah.
Yeah, one of the other people also in our ODE course, like finally saw him for the first time without a mask. I'm like, you got a fucking full on beard. He's like, yeah. I was like, shit.
What, oh shit, it's gonna be like, what time, did your work actually start on like page 160 or something? Beginning is fucking kinematics, yeah.
What are you looking
Are
at?
you referring to the textbook?
We've
I'm
not,
referring to this 240-page PDF that you sent me.
I sent you a 240 page PDF. Yes. Hold on a minute.
You just wanna go over Sean's?
67.
I'm just trying to go.
Megan's
sorry.
lecture notes.
Yeah. I know, no, that's not sorry. I just sent you what we had. I didn't even realize.
Yeah, no.
Don't refer to Wigan lecture notes. Never mind.
I mean, that's actually, it's gonna be kind of useful.
If you think that it's useful in relation to electromagnetism, then yeah, then obviously like included like. But at the same time, I'm not trying to make a person summarize a book in like 3 hours.
The thing is, what I need, I know how to do all these problems. What I need is just like the equations to start from. So like,
Okay.
because like the first problem you can do in a very, very complicated way, which is the way that they make me do it. And I don't want to be like pulling equations that I know from my textbook and be like, oh yeah, use this. And then you go to your fucking exam and he's like, well, where'd you get that from? And you're like,
Well, I mean, if you explain them, it's not a problem because I literally had I like talked to Wigan one-on-one like today, like for deriving UE versus UV, even though they're equal to each other. I'm like, well, why is the electric field squared? Like that doesn't make sense to me. Like, why are you applying a parabolic function to something that's supposedly linear? That doesn't make sense. It's a fucking field.
Unless it was never.
Yeah, I gave up on that earlier, and I wrote the first part, wrote the second part, and then on the equals, I just worked some out. I was not.
so,
Definitely make sure that you got, at least from his notes, I think he talked about, what did he talk about deriving today?
No,
It's gonna be on the final exam. I have some notes and I'll just have to like,
I think
he
it's like,
spent like a whole day driving the wave equation.
yeah, I wanna say it's, I have the notes and I'll just send them to the group chat to make sure that people have them, but it'll be like, it won't make sense because I didn't take like notes. No, never mind.
He
I think
teaches the fact that it's
it's-
impossible to take notes, like in that class. At that point, it's just like, what's the point of even writing things on the board and showing?
He's derived the like angular momentum of light around there.
I'm not gonna lie, that actually made sense because I asked so many questions.
Yeah.
Other than that, I have no idea what's going on in this course.
all right, well, we're gonna, ask y'all to use the calculator part. I want to get some actual physics done.
All right, sounds good.
And then we'll jump back and forth between problems where I'm sitting here, where I'm working, and I'm sitting here. And I'm working. Well, let's do number 11 because it's kind of a straightforward conceptual problem.
Okay.
So we have sphere, uniform charge of 5 microcoulombs.
Should be for the first exam.
Yes, it's first exam number 11.
Is it 5 microcoulombs?
Yes, 5 microcoulombs. The sphere has radius 10 centimeters. Oh, there is 2. And we're asked to calculate the electric field on the surface and at a distance of 5 centimeters. So this is a pretty straightforward Gauss's law problem. That's all we're going to be doing. For the first one, it's even easier. So we can recall, make sure I'm.
Is it the integral of E
E dot DA.
E dot TA. That's the form I think that you guys are given, right?
yes, we are. We're not given
Yeah, okay, so you haven't done it, there's no divergence theorem, it's gonna be, okay, so
Unfortunately.
we can just go straight to this and we can get, this is the easiest way to do it, so that's gonna be fine.
Wait, which exam is it?
Exam number 1, according to him.
Yeah, well, I sent him our first exam, no, with the examples of what we did.
The actual first exam.
E to the
Oh.
vector is Q, is that ENC?
So QENC means charged and closed.
Okay.
So what
So
we're
it's-
gonna do is we're gonna construct what's called a Gaussian surface, and we're gonna do the integral over the area of that Gaussian surface. Okay. For the first problem, we're gonna put our Gaussian surface right on the surface of the sphere, so that all the charge enclosed is just all of the charge.
Right.
The second part, you have to do a combination to find how much of the charge is enclosed within a certain radius, but then the same principles apply. And we'll get there in a second. Essentially, for the first one, what you do is you construct your Gaussian surface. I'm going to do drawing down here. here's our surface. We're gonna put our Gaussian surface right on the surface, which is usually denoted by a dotted line. And so our left-hand side of our integral becomes very, very easy. It's gonna be an integral over the solid angle of E, our radius squared, sine, well, we'll just call it d omega, because that is how you denote the solid angle, which if you guys are unfamiliar, the solid angle is just equal from integral from 0 to 2 pi d phi integral from 0 to pi sine theta d theta. And so that's all I'm doing there. And then this is what you guys might be familiar with. It's going to be the area of a sphere. So we're going to get E 4 pi r squared. This is still equal to for the first case. So we'll do case 1. Charge enclosed is equal to Q total because all of the charge is enclosed within our Gaussian surface. This is the 5 microcoulombs.
Wait, hold on. So you're saying in case 1, did we even go over different variations?
So what do you mean by case 1 is the first 10 centimeters?
Yeah, so
The second case is by
Yeah, case 1 is what I mean by the problem number 1.
I just
11A.
I just want to make sure there's like not some other concept that wasn't taught to us that like in regards to like maybe there's certain parameters.
No,
So
no.
if it's just in regards.
Yeah,
Ignore
so
me.
you're good. All right, so with this in mind, I'm going to rewrite this as Q total because, like I said, I hate calculators, and we're just going to let y'all do that at the end. Over epsilon naught, which is a constant. You have to remember that this is an electric field in the r hat direction. Just so you guys keep track of things. We do know that it's a vector, so you can obviously solve for the electric field here, and we see that Q total is equal to 4 pi epsilon naught r squared r hat. I think it actually only asks you for the magnitude. Yeah, it asks for what is the electric field at the surface, so you really only need the magnitude, which means you can just drop the fuck out.
You could be, yeah, because it's a scalar value. Okay.
Well, it's technically it's a vector value.
Right,
But
but because of how it's asking.
yeah, it's asking for it at a specific point, so it doesn't. You can just tell it tell him the magnitude.
Right. Versus it's
Yeah. So if you plug in these values that we know here, hopefully you get the answer that he gives. That is the correct way to do that problem because it's a charged sphere. When you're enclosing the entire charged sphere, you can treat as a point charge. And that's essentially what we're doing here. We're finding the electric field of a point charge. So fun. The second part is halfway out the surface. And so the neat trick for this one is you're gonna have to do a little bit of geometry. I'll do it over here. So we have a radius of 10, and we have a smaller radius. Our Gaussian surface is a radius 5. We want to write our ratio of our charges enclosed as a ratio of the volumes that are enclosed. So the way that you would write this is Q prime enclosed, which is what I'm going to refer to prime as the Gaussian surface, so the interior surface, divided by our Q enclosed. Well, I'll call it Q total because it's the original Gaussian surface from the first one, is equal to the volume of the sphere. So 4/3 pi r, this is our Gaussian r for the Gaussian surface, r cubed, over 4/3 pi r cubed, which is what we found from the previous one. Obviously, our 4/3 pi cancels out. And we can write our Q enclosed, our Q prime enclosed, as equal to our total Q times r cubed divided by our total radius cubed. All he asks for is that magnitude of the electric field again. Does that make sense where I'm getting the charge enclosed from? Is that 2R? Where are you looking? What this line right here? Yeah, where's the 2R?
No, this is equal E for.
4 pi r squared r hat.
Oh, okay, I see.
What's the upper bound of integration on that sine theta d theta integral?
This on the sine theta d theta, this is 0 to pi.
0 to pi.
Yeah, so interestingly enough, this is always equal to 4 pi. You guys might have, actually, I'm pretty sure that in your lecture notes, he has a whole section on the solid angle,
Yeah.
which is,
Not the first
it's,
thing on
it's
it.
not,
He talked about it for about 15 minutes one lecture.
it's useful because if you have spherical symmetry and your answer doesn't depend on your angle, you can just instantly do the integration in 4 pi every time. So you can just, it makes it nice and easy. It's the same as the trick on a side note. Do you guys know the answer to this integral off the top of your head?
It'll be 1/2 A.
Yeah, it's half the upper bound, so.
It's a double angle identity, isn't it?
Yeah, but if you have sine squared or cosine squared from 0 to something, it's always just half the upper bound. It's like a trick that you can just do and plug in. It's kind of the same thing here with the solid angle.
What is the upper bound of integration for the sine theta d theta up there?
This is pi, this is 2 pi. And the reason that is because when you're integrating over theta, which is the azimuthal angle, you go around the full sphere. But then when you go for theta, which is the polar angle, you only go down once, because if you went back around twice, you'd be doubling your sphere. So you can only go down once. Dandy, right? All right.
I asked that same exact question during calc.
Right, and trust me, I had the same issue with spherical forms, but let's not get into that. It's physics. Hey, how's it going?
All right, so rest of this problem is the exact same as the last one. We get the exact same left-hand side. So we get E r squared d omega r hat omega is now equal to we just found how much charge is enclosed, so our Q enclosed prime divided by our epsilon naught. So now we can go ahead and just plug in. We know this is 4 pi, so we get 4 pi capital R, this is not capital R anymore. You guys should yell at me. This is the integration over the Gaussian surface, so we have to use the radius of our Gaussian surface, the little r, right? So this is 4 pi r squared E equals Q enclosed prime divided by epsilon naught. And so you get the electric field is equal to this Q enclosed prime divided by 4 pi epsilon naught r squared. We know our Q enclosed prime, so this is equal to Q total r cubed over 4 pi epsilon naught r squared r cubed. R squared cancels out with the cubed, and we're left with Q total r divided by 4 pi epsilon naught r cubed, which, if I remember correctly, it's yes. And so the way to relate them, just as a general rule, if you get this question and you're trying to save time, is that the electric field at an interior point, so where it is interior point, is equal to the electric field at the surface times interior radius divided by total radius. It's just
So for the electric field, it's based on whatever inner radius that you have over the overall radius.
okay. That's just like another one of those like neat kind of tricks that if you recognize that this is a type of problem you're being asked, that you want to find the electric field at a interior location of a charged sphere. You can just, if you find the total electric field at the surface, you can find the location at any point inside by just multiplying by the ratio.
Is so
location.
it's epsilon naught by the whatever version of r that you have, so like how far it is from the center cube, and then you have the overall outer radius of r cubed. Is it specifically based that it's r cubed because it's a 3D system?
So you're talking about the R cubed here?
Yes.
No, so if you guys remember, our units obviously have to be what, volts per meter, I think is the units of the electric field. And so in order to get that, your dimensionality, you need to have 1 over R squared, or 1/meters squared outside.
Mhm.
And we have R over R cubed, so dimensionally, this is still 1/r squared, the same as previous.
So,
However, the values of each of those radiuses are different, so.
Okay.
Remember dimensional analysis, we can do this if you guys want. So
it's up to them.
charge of, or units of charge is coulomb, 4 pi's unitless, what's it called? Like that's what, coulomb per meter or Newton coulomb per meter?
I think it's Newton coulomb.
I think it's Newton coulomb per meter. So this is over Newton coulomb per meter times meters squared. So again, meters cancel out. Or is it just Newton per meter?
Big R is the radius of the.
I think epsilon is Newton per meter.
Over epsilon, okay, you actually, you're right.
I should know this. It's kind of my job, but.
Wouldn't it be Newton on the bottom, because
So everything you
Newton
see.
for
on the
Newton.
side,
Q times
left
D,
half
you
the
get
board,
Newton flat.
part A, where it's asking what the electric field of the surface.
I think it is Newton.
is.
Vacuum
And the second
permittivity
part is it's asking,
is,
what is the.
Wouldn't that be
electric field
epsilon
of the sphere at radius of 5?
And what's the units for that?
So what we did is we
That's what
found,
he's
we found the
looking
charge of the surface by including the entire surface in a Gaussian surface.
isn't it C squared?
And then to find the inner Gaussian surface.
For the permittivity of free space?
That.
This is what the.
Because if you do Q times G, they're supposed to give you.
Yeah,
Newton
we
flat,
just took the
so you get
ratio
your
of volumes of the outer sphere and the inner sphere versus the ratio of charges enclosed.
it's Coulomb squared Newton per meter squared.
Hey, I got that.
Coulomb squared Newton. So what you're left with is both of these cancel out 1/Coulomb. So you end up with 1/Newton Coulomb. Let's see what is Newtons are kilogram meters per second squared. We want to find, where's your exam? So we need to have coulombs. What are the units of talking coulombs? I know you can really, I know you can.
Fucking halfway through our lecture, I realized that half people who discovered shit physics didn't know shit about physics. Like,
Yeah.
Right. It's just. So you know,
This is bullshit. People later on just put it all together.
honestly.
Oh shit, I need that. So units. Learn your units, don't be like me. So
Yeah.
if we recall, a volt is equal to a kilogram meters squared per second cubed area, or it's equal to a kilogram meters squared per coulomb second squared. So I think we're going to use this one. So if we plug this in, we're going to have
Don't die. All right, bye.
over kilogram meters, so it's in seconds. Coulomb. No. So I'm just checking the units to show that this has the correct units, and then I can show that the R over R cubed is the same units.
Okay.
But I believe it comes down to this when you simplify it out, which is seconds coulombs per kilogram meter, which as we can see is just, I have it flipped. So right now I have meters
Yes.
over volt. So I did something wrong, but that's beyond the point of the actual exercise. If one of you guys take the time to do that, let me know. Be interested to see the unit analysis for electric field. But essentially, what ends up happening is if we ignore this right here, part of it, and we have 1 over R squared, which is the usual electric field dependence. Over here, we get R over R cubed, which dimensionally is still just 1 over R squared. Because they're both meters over meters cubed, we get 1 over meters squared. That's the point that I was trying to make. kind of missed the point, if you will. So that, I think, was the entirety of the first problem. So let us look at the second one. Anybody have any questions about that one before I go to the next one? It's a pretty direct problem, if you will. It's kind of just like identify that this is Gauss's law and work. See, the next one is. Yeah, a cube or isolating material shown on the figure has one corner orbited. Each side of the cube is like 0.08 meters. So the top face of the cube is parallel to the XY plane. Okay. Interesting.
I would definitely ask if we have time, to definitely go over, well, not necessarily 13, but 14 for sure, because these are capacitors and capacitance.
Yeah, I was gonna try and do all the open-ended ones before I went to the what's called the multiple choice. And what I was gonna do for the multiple choice was I was gonna ask if you guys had specific ones that you wanted to cover, since there are.
I'll leave that to the room because I don't have an idea, and probably it's a better idea than what I had, so.
Let's just do 11 through 14 first in order, and we'll call it a day, or we won't call it. You know what I mean?
Yeah, I know what you mean.
Okay.
I don't get it.
This is a really weird question, but is anyone? I'm gonna clean this up for us and then afterwards.
So
Most things should be open.
Pizza Hut will be closed. The sushi place will be closed.
And the web
The
stage.
juice bar will be closed. Subway will be open.
Yeah, Subway's open until 7.
Chipotle's open, sorry.
If you want food, I'm pretty sure we could chill, like, we'll be fine.
Yeah, no, it's not what I'm not what I'm heard. He asked what's
Yes.
open at the end of this.
Oh, shit.
Shake.
You're asking what's.
Steak and
That's
shake.
pretty-
Second shit, you have to wait 45 minutes for your food.
That's why you
Bro,
drunk.
don't get me started.
That's why you-
No, let's not get started with that, because I got a whole rant for that.
I'm about to say, so do I.
I'm so mad at that thing.
So it should be.
Is that juice?
No, Grubhub is the reason I had to wait fucking 2 hours for my friend to get fucking chicken tenders, because they had 178 online orders.
What the fuck?
Yeah, just because she.
I don't know what sandwich you're going for.
It's right there. That shit right.
So why did they stop opening at lunch?
That's
That's
a
really
big question.
Oh,
It's
so they don't have
weird.
enough people to work there, that's why.
That's why they have such weird hours. It's
No,
almost
but
like
actually, it's funny.
If you-
Some of the people from Chick-fil-A actually go to
Yeah,
work
some
over there.
people.
I think they
literally change teams.
Right.
Hey, it's how you get that bread. It's about time. It's about power.
Follow the double, when you get the Chick-fil-A.
Oh, shit.
In order to get an application for Chick-fil-A, you have to know how to work the fryers for steak and shakes. Quite experience. Question, do you know how to make a shake? I should play, yeah, still.
Yeah, the Chick-fil-A shake is mild.
Here, Chick-fil-A, we used to know how to make nuggets and these banger ass tender and burgers, but aren't y'all a chicken joint? Yeah, what about it? Like.
Is it damn good burger?
The whole thing is eat more chicken. Teaching you.
Eat more chicken, burger, steak, shake. Like, hey, yo, I want a burger real quick. All right, shit. I could go for some almond chicken there right now. I'm not even gonna cap. Like,
Oh, yeah, they're,
You like that almond chicken?
I do.
Oh,
Do you not?
Wow, it's good, it's pretty good.
It's breaded. It's good. It tastes.
It's just like having the consistency of like sweet soy sauce.
Look, see, here's the thing. Is like for me, for like fucking at least Panda here, like you gotta eat it right then and now. Cause like I tried to like it's like I'm gonna take this shit home because I got too much chow mein. I'm like, nah, this shit is not good the next day. Like not like regular Chinese food. Like what the fuck? Like-
assuming it's regular. trend.
like Bushula, man, girlfriend, Bushula. Sorry, I took Mandarin in high school, so. I'm just- So it's fun. I took Spanish, hey, I took Spanish too, as well, like.
Oh, so do you guys know, like, so like for your guys' degree works, was y'all Spanish like not unchecked? You know, I did it in high school.
No, mine counted.
How far did you go?
I did 3 years of it.
2 years Spanish, 2 years Mandarin.
Yeah, I did 3 years of Spanish.
3 years, I think it should count.
Yeah.
Yeah, you should.
Mine
It's
is still
either
counted.
3
That's
years.
why I haven't talked to my.
It's either 3 years of one or 2 of 2.
You should talk to your.
Okay, I still. But I mean, like,
still
yeah, you're a
basically
minor
know it.
symbol.
You don't wanna take.
I'm not gonna lie, I stole
You don't
my
take one
Mandarin,
right
I still have it.
People like,
That's right, I'm
Right.
recording,
Yeah.
fuck you, philosopher, like, I took my
But
book.
like, you're a minor sim engineer, right? So it should count like in 3 years of the 2.
Yeah.
Okay, alright. So you saying you give you no bullshit, if I go up there and be like, what's up, what's up, it's good. Good.
Was that like a second example?
So again?
You said
Exactly that
No, but I can send you the second example if you have time, if you want.
Well,
No, I mean, that makes sense, like, to go over those kind of problems.
frankly, I would prefer to just go over the practice final that he has up.
That would be a good idea.
Yes,
too.
two.
Alright, I'll start.
Oh, he has two
I
practice
think there's
finals up?
one under.
Yeah, I was
Yeah, I would
Dr.
like that
Bloom, give me a second, I
There's
will,
one under course documents and one under the sample exams.
I'll give
Do
you,
the sample
which,
exam.
Are they the same one?
I don't know, but just do the sample exam.
the final exams for
Yeah,
2017?
No, it's the
If you go
sample
to the
exam
exams tab.
under the sample exams tab, there's a sample final. And under course document, there's a final
I'm still
for
currently
his
working on the
his
master's
2017 class.
Is it?
That
is it-
stuff
is it-
takes
is it-
way
it's
too
Sandy,
long.
right?
Because,
Which,
and
which
it's funny
final
because then
final?
the thing is, the worst
Just
part
do
is,
the middle
I know
one.
this is so bad, right? But in order to
Yeah,
get
it's
the
the same as our
homework done,
regular
I had
test.
to
You know
get
what?
separate.
I
really did. I didn't have a
The
choice.
first one might be just.
I also so much that.
And then-
The first one might be-
And then
Bro,
none of
exactly
it,
what I'm saying.
then almost none of it shows up on our exams.
Yeah, you wanna see
That's
something
why this lab should be
tragic?
counted for more.
Per question. We have 3 hours.
Mainly because you have to read all that shit.
Oh, well, the middle one sample exam gives you answers.
Right, so that's, I'm gonna add that.
That's the answer key. The number 2 out of 2 is the ones, the problems you work out, and then the top one is the.
Tragic, you know, homework, I saw.
That's literally what mine looks like.
25, 26, 27.
How many more do you have?
I signed 32.
Alright,
How many
I got
more?
I'm all the way up to 21. I still have 21 to finish.
I finished my unit just today, and this is all.
Yes.
You're in it.
Oh my god. No,
Yeah, it was not.
Yeah, that's what I had you check.
Yeah.
Check it this
if,
Like,
like, unrelated, to you have time, since you're also,
Like
the
2 weeks ago,
lab.
I only had like 4
Professor?
assignments done. And I
You have
took his
questions about
practice
that?
final, and I got 47 on it. So if I do all of
Out of 50?
all the assignments, that's already a pass.
Was that a 50?
No, it's out of 100. But if you do all the assignments, you need a 40 to pass the class. It's a pass.
You said you only need a 40?
Yeah.
Like a 40 is a, oh yeah. Wait,
Yeah,
that's a
you
B,
do-
right?
No, it's a pass fail class.
so,
Wait, this class?
so you're
No,
going from,
no.
you're going from the exam, exam 1, right?
Yeah, well, so I think
was about
it's,
to
well, it
say.
might not be, if you guys wanna do your practice final, what we could do is, since, we're moving pretty quickly, we still have 2 hours. We do these 4 problems and we go to that rather than multiple choice.
That works. for
Yes,
mine.
that's
Works
what
for me.
Yeah, bet.
Because they have the multiple choice answers already on Blackboard as well.
Yeah, that's all them on the, what's it called here too, and they're not, from what I read, they weren't terribly difficult problems. The ones that are, this one's frustrating because you have to be careful. When you traditionally think of calculating charge enclosed, you think, oh, like on the last problem, we knew the charge enclosed was a certain amount, but say we wanted to calculate it, where do we start our electric field from if we want to evaluate that? And the only way to truly do this is you have to have the electric field start on the one boundary and leave out the other boundary. So you can almost think about it in terms of like a flux. So the way to find the electric, or to find the charge enclosed, is to have the electric field go through all possible location where the charge is enclosed. So in this case, we're going to define our electric field, and it actually gives us the direction and the magnitude. But where do we start it is at the, which he calls this the ZX plane. So we started on the ZX plane, and we have our electric field come up through, and it's a magnitude of 3290. 3290 y j hat is equal to our electric field. That is, and so this is just another Gauss's law problem, where we essentially are going to be creating a Gaussian surface here at our. I'm drawing this terribly, but it's what I'm really trying to do is I'm trying to make this Gaussian surface be just the top piece of paper of the cube, encompassing it's this Gaussian volume, right? Where in reality, this Gaussian surface has 6 intervals corresponding to each sheet, 4 of which are infinitesimally small, and the other one is counteracted completely by the one at the bottom. So the only one we need to do is the one at the top. Actually, interestingly enough, we can span this all the way down, but we don't care about that. All we care about is finding the charge enclosed of this cube. And the way to do that is Gauss's law, like I said. So you're going to take the integral over A of E dot dA is equal to our charge enclosed that we're trying to find, charge E and C right away epsilon naught. And so we solve for charge enclosed. Equal to epsilon naught integral over A E dot dA. And so now we need to just think about what is our area of our surface. It's just the area of the top side of the square. So I'm going to denote each one of these sides of size A, just because, actually we'll use S. S is nicer. So each one of these sides is equal to 0.08 meters. And so therefore now our answer is equal to times our electric field times our area, which is just S squared. And then so now what we need to do is plug in our E, which we can conveniently rewrite as, so we know that each one of the sides is the same, so Y is just equal to S at that boundary. So therefore our electric field is just equal to 3290 S, or what I'm going to call this number, we'll call it, I don't even think of a variable.
I don't know.
W shit. It's N. It's NS. So N is equal to 3990, whatever the number was, 3290. And so we can plug that in down here, and we're going to get epsilon naught NS cubed, which is equal to, I don't know, whatever the Q would be, just Q close. You can plug this in, and it should be the correct answer, I believe. If somebody has a calculator, they can.
Where are you getting N from?
So N, I'm defining N as the number in front of the electric field because like I said, I don't like writing equations in terms of numbers. Unless it's like 2. 2 is fine. Think of 2. But do you have any questions where things came from? This is another really rather short problem.
How'd you get S cubed?
So you have the area from your Gaussian surface, which is S squared, and you have your electric field, which is defined as 3290 Y. But where the location of our Gaussian surface is at Y equal to S. So our electric field is equal to 3290 S. And so you have S times S squared, which is S cubed.
You have like 3 different sides you're working with, like your Z, your X, and your Y.
He's not ancient, so he knows how people learn this thing.
I'm saying you said it's cubed because why again? I'm sorry.
So it's cubed because we have one S in our definition of E that he gave. If say he gave the electric field as equal to 3290 Y squared, then it would be S to the 4th. That one of these S's is just coming from the fact that he gave you an electric field that depends on a linear location of Y.
Right.
And the location of Y that we're at is equal to S times cubed. They're all the same size, right? We're at S high. Right. And so that's one S is coming from there. The S squared, the other 2 S's, if you will, are coming from the Gaussian surface, the area that we're integrating over. So we're integrating over that top area that has area of S squared because it's an area squared, S times S, right?
Mm-hmm. Okay.
And so S times S times S is S cubed. Right. Oh, you kicked out, sorry. No, does anyone have any questions? Again, that's another just Gauss's law. I have a feeling that based on how this is going, this test was mostly Gauss's law for the first test.
Yeah.
So I'm assuming that until we get to the
That's all we
compact,
got to in the first test period.
Yeah,
makes sense.
he really sped up the second half.
And he's like,
Yeah,
oh, shit, we have a-
So
we
if
have
you
a-
look at
We
the
did all of optics in 2
calendar,
days.
if you look at the calendar for his class, he was supposed to have an exam like 3 weeks into class. And then another exam like a month after that,
He
and then
changed
have
our
like a
parameters.
month and a half
12 hours.
before finals without an exam.
Love it.
Yeah, he turned everything around and we took like a month and a half before the first exam, and then we had 3 weeks before the exam after that.
Which you
Now
would
we have,
think,
like, 3 weeks
think
Yeah.
finally on.
Between those.
Yeah, that's why.
2 weeks, I think it's 2 weeks.
No, it's 2 weeks, you're right.
Yeah,
Not
2
even-
weeks
not even 2
between,
weeks, He changed what we needed
between
to
the
study
second exam
12
and the
hours
final.
before, because he fucking emailed us.
Well, and I also love, he's like, study chapters 27 to 28 or whatever.
Did that change?
And every
11
single,
hours before.
Yeah,
every
that
single
changed,
piece
yeah.
of reference we had is a different chapter too. Shaw's is one chapter, the lecture notes is one chapter, our textbook is another
And
chapter.
then don't even get me started on
And
What
he
is
says,
27,
he
28?
says, I'll tell you what's gonna be on the exam, and then I ask what's gonna be on the exam, and he says everything.
The fuck?
I'm sorry, what?
What
the actual-
Give me like 2 minutes to solve this problem real quick.
Yeah, no problem.
They're fine.
Streets.
I'm sorry, right, yeah, like you said, we got 2 hours. We're good.
Like,
I prefer to have the answers to the problem and like understand it than versus.
Everybody.
That's what I'm saying, like, I'd
Everybody
rather
at
take
my
like,
table is
I'd
just
rather take an hour.
Because
and
we're all-
make one
because
problem.
which table
All right,
do you
guys.
got?
I'm all the way in the corner.
Silly question. What is the equation for the potential energy of a part? Is it KQ over R?
It's either KQ over
So,
R.
I have to make this chart every time, so
I think
reference for you guys. This might be helpful.
Chart.
So vectors, scalars.
Q1, Q2 over R.
So potential energy is 2 charges?
Yeah.
That makes sense. I should have thought about that because the voltage is 1 charge. And
we
so-
just did this in class.
Force
Yeah, we
is
did.
equal to KQ over R squared. Electric field is equal to KQ over R squared.
Lightning bolt for.
Or, yeah, over R squared. Then vector, and then this is potential energy is KQ over R, and voltage is KQ over R. So,
You have KQQ over R for V.
no, so that's U at the top. So
So-
the potential energy of the part, like a potential energy of a system
Right.
has KQQ over R squared or over R, which I should have thought of because in order to have potential energy, you have to have 2 particles. So I don't know why. Anyway.
Capital Q over.
Yeah,
Yeah, but I'm just QQ. I'm just referring to as 2 different charges. You can have a potential difference when you only have 1 charge, which is your voltage. And then these are obviously vector directions. I'm just going to call it EI. Just to note that they're vectors.
I don't know.
E.
Well, I know what it means, but in the context of phase, red pill.
I know red pill and black pill means.
R squared.
KEQ over R, KEQ, and then U over R.
It's the same thing, but one's R squared. And one's vector.
I'll transcribe my own notes and it's like you can scratch, but like, I'll do it so it's legible and I'll send it to the group chat.
Sorry, is my handwriting knowledgeable?
No, it's not yours, it's mine. It's
Oh,
like,
okay.
I'll take up the mantle of, unless someone else is like, they're definitive on what's going on. They're like, hey, my notes are better. I'll take your word on it.
the only class that I can take the notes for is math.
That's
Right.
easier because you can break it up into equations.
Yes.
If your
Yes,
does your handwriting turn into like this halfway through? You'd be like, and therefore,
Well,
Yes.
yeah,
Yes,
three
yes.
would you,
I just use 3 dots.
that the equation leads to
Yeah.
2x plus b. And it's like, that's actually readable, but that makes no fucking sense. Yeah, that's the cursive math.
I
It's
tend
already
not,
getting to the point where like, right?
I tend not to use sentences when I take math notes.
Honestly, yeah. If
I
they
just-
are
I didn't
sentences,
like
they're
to
short.
until all my professors made me for like turning homeworks. Actually.
I mean, hell, you're in
They
my
made
ODE
you-
course, so like,
Well, it's
I don't know what you put for sentences.
Who do you have for ODE?
Raja.
Ruha Zhao, and he is the greatest. I love that man.
Yeah, he's
I'm
fun.
on them.
What
is that?
I'm taking Jones.
He's
I'm
like,
taking Jones
yes,
next
yes.
semester.
Jones, I will say, is objectively harder than Zhao. I've taken both, and I've had a friend who took both. And he looked at our final for Jones, and he was like, "I can't solve any of this."
Right. Yeah.
But Ruhai will make it simple.
I got a bunch of recommendations. for
I got a
Jones.
Why
bunch of
can't-
recommendations for Joe.
He just keep the answer in terms of an equation. Sorry.
If-
right.
I think
There's like
you,
a-
I think you of all people would be fine in Jones, but I would
Why
recommend,
me
I would
of all?
recommend Zhao.
Because you're not done.
I had to
What does
retake,
that
I had to
mean?
retake one of the quiz 8. That man was slumped in his own fucking like room.
Oh, you're on.
Yeah. No,
I see it, I was like, is that?
well, like, I took him for Calc 3, and like every time in the day, over the summer, he was like, "Oh, very sleepy." Like he fucking like his whole life goes on around him when he fucking lectures, and I find it funny as shit. Because he's got his cat, he's got his phone going off and shit, and it's just like he gets tired because when I took that quiz, he was like, "Come on at 4:30." I'm like, "Okay, cool." And then when I showed up, his lights were on. He was fucking slumped on his desk. I'm like, "Hey, you know, it's like because he fucking wakes the fuck up, turns on the lights. She's like, oh yeah, here you go." Like, and just he goes back. He goes back to what he's doing. He's just sleeping. I was like, "Oh my god."
He was doing that during the exam the other day.
He was just sleeping during the
It's just during the
exam.
exam. He was like,
How do y'all feel about that exam? I feel either I did well or I did terrible.
Oh, no, I feel like I did pretty, I feel like I did
the
pretty
only,
well.
the only problem that messed me
The
up
only thing
was
was like the last thing was like.
IGP with the Laplace transform of 5 times the step function of U.
I love the.
I think
I said you're scaring me with those big words.
Yeah, I was about to say, I have no idea what's going on.
See, with the
Yeah, I
last,
was, I'm like, yo, I wish my mind sim engineering class could switch exam.
Yeah, I
pages.
understand.
That's on Friday.
I got one.
Yeah, I told one exam was no big.
I at least know what Laplace is.
All right, we have another problem. We can.
You know,
all right, let's go.
What?
Initial value problem.
IGPs. I got the second portion right. The
This
first-
problem is really quick. It actually took me longer to plug it into the calculator than it did to actually do the problem. So,
Good to know.
granted, I am calculator impaired, so.
Me too.
This is a conservation of energy
Very
problem.
technical.
My question still remains.
Yeah.
Sure, let's say that. Yeah, sure.
So, for conservation of energy, we know that at the beginning of our system, we have a proton and a proton that are some distance apart.
Huh?
Yeah, that's recording.
Is this the final or the first exam?
I treated this as a proton and electron. Give me a second.
We're still working on the
That's
first.
why it's so simple.
No, so I had the distance kind of messed up because I was treating it that they were going to each other, but you can't have the protons, so they go away from each other, and he even says that. And I just didn't read the second part of the problem.
We're only in the.
Alright,
So,
like that.
Yeah, I'm writing Ben.
I feel like, it was funny because it was like the last part of the test for the differential equations test. It was like, I couldn't even get to the, we have to do like A over insert number over here. So,
on the last problem?
yeah, like the first
What
one.
we had to do was
The second part.
Huh?
The second part or the first part?
The second part.
The second part was easy. Well, I say that. I should be wrong. No, it's not easy if you don't know what's going on. But only because he had his if you went over the review and the quiz review, then you were good. That's how the only reason I was able to solve the second portion. Because the first one, I was I can't prove that this equals this because of his notes.
Oh no, I could, use a DK over D and do like the D over.
Yes,
T.
your first exam.
about that, which is
Yeah, this is two problems.
The last.
Yeah, I said I know.
You had to do
So I saw So two protons, it's like, oh, two particles, they're gonna collide, that's what they want, because that's the problem they always
The
ask.
opposite of what we asked.
Yeah, so what's gonna happen is you put two protons close, they're gonna go away from each other, he wants to know how fast it's going at some distance. I was just like, oh, they're two particles, he wants to know how fast they are when they collide, and like, that's what they always ask. So like, that's just what I did. Yeah.
So have you taken Calc 3 yet?
No.
I've already taken that and finished it.
I don't have to. You don't have to take.
Oh.
What's your major?
And
Mine, some engineering.
like civil engineering.
No, modeling simulation.
Yeah, I'm in Calc 3 with Dorpal right now.
Ooh, I love Dorpal.
Oh man, so good.
I had him for complex variables.
Yeah, I got lucky with him because he normally teaches high level math classes.
Yeah.
But just this one semester, he's teaching Calc 3. And I managed to get him Dorpal.
Who?
Mark. Dorpal.
Wait, are you MC?
Sorry?
Are you MC?
Henny.
I'm probably gonna have one.
I always say the Canada MC.
But yeah, if you're applied math, you'll probably have Dorpal at some point in time. Such a good teacher, man. Like,
I've always picked 4 teachers. I don't know why.
second bottle?
Second bottle, and started digging it.
Oh my.
Yo, that's a lot of juice. I don't even know if I can finish one. That's not second bottle either way. That's the third. All right, let's get back to physics. Hopefully you don't got a job.
I don't.
Okay.
I'm literally walking to someone else's place to help one assignment after this, so I'll be fine.
I'm gonna be doing mastering assignments and statistics, all that.
Oh, yeah.
I've been doing physics.
So,
I've
yeah,
been
if
doing
you
physics
do
homework
stay
all day, which I
applied
need to send to you, by the way.
Look for class.
Yes.
I mean, I'm rocking like a 94 in Calc 3.
You said, so you said that.
And we bombed the first exam.
Yeah, so what you're gonna have to do, I can set up the equation and then we'll just, we can do it together and you guys can yell at me when I don't do something right. What I like to do is I like to solve the problem before I talk to you guys. But we'll do it together. You can yell at me.
Talk us how you're thinking.
So
Yeah, that, honestly, your thought process, because you're a actual major within this like degree, that's our problem.
sure, I'll talk you through. So what we're doing here is we're gonna have a start position and an end position. We have two protons that are this distance apart. We'll call this D1. And then we have two protons that are this distance apart, which is now D2, right?
Okay.
And so conservation of energy, at this point, our kinetic energy is equal to 0. And our potential energy is equal to some value that we're gonna find, right?
So does the KE increase since they're becoming like the distance is increasing?
Yeah. So what's gonna happen is since they're moving apart and protons feel a repel from each other, what's gonna end up happening is some of that potential energy is gonna be lost in the form of kinetic energy, which is going to move them apart from each other. And so our kinetic energy is no longer 0 for this system, but our potential energy is, it's less than this. So what I'm gonna do is I'm gonna write that it's less than PE1. And so that's how I would identify this type of problem. I'd be like, oh, we're gonna have initial system, second system, conservation of energy. So the energy in this system has to equal the energy in this system.
Right. The second potential energy is the first potential energy minus the second kinetic energy, right?
Yes, that is what we're gonna get at. As I was taught back in high school, what he called the most valuable equation, which is just called, it's conservation of energy. So if you have kinetic energy plus potential energy plus angular kinetic energy plus gravitational potential energy plus
The hell?
electrical potential energy.
I was about to say, I took physics.
Yeah.
I'm not hearing about half of this.
Yeah, and so if you add all these up beforehand, they have to equal all of those same values on this endpoint, whether or not they're 0 at the second point or not. The energy at the beginning has to equal the energy at the beginning.
Right.
And so what we can write an equation that looks like this. So I'm gonna stop writing PE and KE, and I'm gonna drop into the traditional physics notations of T and U. So T is gonna be our kinetic energy. So we're gonna have T1 in the beginning part is equal to T2 plus V2, right? And V2 is going to contain our 1/2, well, actually, it's the total kinetic energy of the system. So it's for two particles, it's 2 times 1/2 mv squared, right? Because this is that's just the kinetic energy of a particle, 1/2 mv squared, right? Or p squared over 2m, if you're familiar with that form. We can write this both ways, just so you guys can keep track of things. Are you guys familiar with that form for kinetic energy?
Is that p squared in reference to momentum?
Yeah, momentum. So it's mv squared over 2m reduces to 1/2 mv squared. But I don't know which way you guys were shown kinetic energy.
Any information is good information on it.
Right, pretty much.
That's classical mechanics. That's not, you're not gonna have to know that for your exam. You just need to know this and you'll be fine.
You say that, and here we are.
It's just a neat tidbit. So we're gonna need to solve for this v eventually. But that requires us to solve this equation for v in the first place. So we do T1 minus T2 equals V2, which is equal to our 2's cancel out nicely, is equal to our mv squared. And so now we can conveniently write our equation for v is equal to T1 minus T2 all divided by m. Marker starting to die on me. All to the 1/2 power, it's the square, right? So now all we need to do is find that potential difference, or the difference in potential energy. So this is what comes in and why I was asking earlier for the equation that I've now erroneously erased from the top corner. But T1 is going to equal our K, Q1, Q2 divided by our, in this case, D1, right? Because it's the initial kinetic energy of the system. Our T2 is going to equal our K, Q1, Q2 over our D2, our second distance in our equation, right? And so T1 minus T2, yeah, that should be the right form. I'll Google it after this and see if I'm right, because most of these questions will be online.
Should this be 1 over D1 minus D2?
Yeah, it's,
Never mind, you're writing it out now.
yeah. I'm just trying to remember this form from when I took this class. So then you can go ahead and write our velocity is equal to K Q1 Q2 over M times the quantity 1 over D1 minus 1 over D2 to the 1/2 power. And because I'm not sure if I kept track of signs properly, I'm going to slap an absolute value in there. Because
of point charges and.
no, that it would be positive. It would be good because
Yeah, it has to be
D2
positive
is less than
value.
D1, so it's going to be a positive value. But I think that's right. If somebody is good with a calculator and wants to plug in that value, we can check it. Now we can cross check. You should get 2.9 times 10 to the 6th. But that's my approach to the problem. That's how I would do it. Did the logic make sense to everybody there? I feel like it's an important concept to get conservation of energy.
What is D2? Where does the 2 come before that?
Oh, so it's the total kinetic energy of the system. There are 2 particles, each with kinetic energy 1/2 mv squared.
Okay. Oh, cool. Thank you.
So what does T represent in this case?
T is the potential energy,
Okay.
which actually, I kind of fucked up my variables, because I'm pretty sure that you want to use
You use U.
U for potential energy,
Yeah. It's weird. If you use
T
U-
for kinetic. I think I flipped them, but
We talked about in class today.
it doesn't really matter. It's just a variable.
Yeah, in relation to that.
I'm gonna make a note, so you guys, this is
T
kinetic,
equals U.
this is potential, because,
What are the distances? Does it tell you?
oh, yeah, I can tell you that. D1 is equal to 2 times 10 to the negative 14th meters, and D2 is 5 times 10 to the negative 14th meters.
Wait, you said D2?
Yeah.
Yes, D2 is 5 times 10 to the negative.
Yeah, I get like 2 million meters per second. Something like that.
2 million.
That's close. It should be
Yeah,
times.
I was gonna say-
Yeah, 2.9 million is the correct answer.
Yeah, it's like 2.9 times 10 to the 6, so yeah.
Which actually, that makes about sense for 2 protons repelling each other. So.
It's fast.
All right. All right, time to solve another problem. We have one more problem, then we're gonna go to the, what's it called, exam?
The final.
Yeah, your sample finals.
The beginning.
Don't ever find it weird that, Rubai, causes, the exams on midterms?
No,
No, there's, I mean. Professor Witten doesn't do.
most of my exams are just called midterms.
Yeah.
Yeah.
It's the particular solution. What is that? When he said, what is that, like during the lost transform, I was trying to hold it so hard to like not lose it. Cause I'm just like, yeah, that's what I'm saying. It's like, what is that? And you multiply. I love Ryan so much. Like he's a good person. But like,
I mean, he makes the class entertaining, so you make it so you make.
so you learn shit because he's entertaining.
Right. That's what
That's
they're saying.
that's what I told him today is like Ruhai, unlike other professors, like he makes the class entertaining by accident. But it's funny as fuck because it's Ruhai. So
The first two parts of the last problem are really, really quick. They're like plug and chug problems.
okay.
The third one, I didn't remember the equation, energy density between plates. Energy density would
Isn't
be,
energy density equal to the integral of E dot dA?
that is not true.
Isn't it 1/2?
Isn't that flux?
That sounds right.
We just went over. it.
I can confirm that.
So it's 1/2. So it's 1/2 the permittivity of free space
Times the field square.
times
Yeah.
it. Okay, so
I mean, you had a question of why the field.
why is the field squared though? Why is it a parabolic one, not a linear one?
Oh, did you ask him to derive that for you?
No, because we didn't have time. Like
His office hours are still going.
He skipped our break today.
His office hours are still going.
If y'all are curious, while people are working in my lab tonight, I can try and run through like a brief derivation for the energy density in terms of the electric field and see where the square comes from, because I don't personally remember myself. And then just send it to you and you can distribute it. If I don't get anything, if I don't get a solution, just assume that I couldn't figure it out. All right, so let's do this problem super quick.
Thank you.
So then we can move to your final.
What if he goes down here?
Damn, I'm good on that.
Yeah, no, really. Oh,
I
I
mean-
mean, you guys hundreds.
Yeah, having fun. I'd actually like physics.
Yeah, he gives us especially credit for this. Take it for.
Wait, what did you get?
People are averaging 70s. I did not get that.
I mean, I got like a 68.
All right.
So that's why I'm so sad.
So for the last problem of this first exam, what number is it? This is number 14. We have a parallel plate capacitor of 2 circular plates, right? Their radius of each plate is equal to 10 centimeters. I'm just gonna refer to this entire plate's area as A, because I'm tired of calculating things. But as you guys are aware, the area of a circle is pi r squared. So plug in 10. That's how you get your actual numerical answer.
Did you just say 9?
And so then the distance between here is D, which he gives us 1 millimeter, right? And the first question he asks is, what is the charge on the plates? The first thing you need to do is find the capacitance. As those of you who are in my lab might remember me saying, capacitance is completely, anybody remember? geometric. It doesn't depend anything on it doesn't depend on the actual like potentials or the charge in the system. It depends solely on the geometry of the capacitor.
All I
And
remember
so
is relevance of line.
our capacitance is immediately we can write down as epsilon naught A over D. That is the capacitance of parallel plates.
Oh, yeah.
So we know the capacitance right off the bat. It's just epsilon naught A over D. You guys remember the equation Q equals CV. Also, by the way, he gives us our potential is equal to 100 volts. Just a reference. And so now we plug this into here, and you see that Q is equal to epsilon naught A V over D. You can plug your values in, and you'll get the correct value. This is a very plug and chug problem. This one's going to take literally like 10 minutes to explain. No, that's about it. The second problem is even easier. We don't even need the result from the first one. If some of you might also remember from my lab, when we did the equipotential lines, how did we discuss magnetic fields or electric field strength? What was the equation for electric field strength? No. Electric field, actually, electric field is 1 over r squared. But volt over distance, right? So it's absolute value of V over the absolute value of D. If you guys remember that, also we also wrote it as delta V over delta D. The other way we've seen it, it was the easy way to calculate it. It's all we need in this case. We don't need to do the fancy form. And so we can immediately just say that this is 100 volts divided by 1 millimeter, which is actually gives the correct answer that he wants, which is 100 kilovolts per meter.
What was the distance derived?
It's a 1 millimeter.
Oh, he gave the distance as 1 millimeter. So that's the electric field. And we've been so kindly reminded that the energy density, which I don't even know what correct variable that is.
It's U.
It's
Yeah.
U.
He uses U.
U sub E.
Could we trick? Well, there's a cool question. So we'll do.
Which is why I thought it was weird, because he uses
I'm curious. So
he uses
well, the quick way to do this is just use the equation that we've been so kindly given is epsilon naught absolute value of E squared. Take this value, plug it into that.
nice.
But since now you made me curious, we're going to take an extra 3-minute detour here. We know the potential energy of a system is KQQ over R, right? So is this equivalent? If we treat Q as this on each plate, right? Can we write this as, so this is 1 over 4 pi epsilon naught, epsilon naught A V over D, epsilon naught A V over D over 1 over D. So when epsilon naught goes away, area is pi r squared, or in this case, no, it's a different r. We're good. Okay. So we're gonna get 2 pi's, 1 pi is gonna go away. We're gonna get 1 over 4. There's a pi over 4, because there's a pi up front. R to the 4th, V to the 3rd, V squared. Is that going to be any bit close to what we had originally? So this is going to be. Oh shit, there's an epsilon naught too in the numerator.
That would cancel out a lot of your things.
V over D. All this is like so crazy. Oh, it's close. What if that's how you get at it? This is the correct way to get the answer. That's all you guys need to actually know.
Okay.
But now it feels wrong to just leave the understanding. Okay, so this actually can answer our what's it called? Our derivation for where E squared comes from. And so we can denote our energy density, so UE is also equal to E over V. We think about it as how much electric field per potential, which is kind of useful. But the reason you get the E squared is because this comes from 1/2 U equals 1/2 CV squared, the potential energy of a capacitor. And then see, I can really just follow the derivation. So we know the capacitance is equal to epsilon naught A over D, as we have just shown. And voltage, if we solve this equation for voltage, is equal to ED. We therefore get left with, we plug this in, so this is going to be E squared D squared. So we get 1/2 epsilon naught A over D E squared D squared. So one D cancels out. Interesting. Okay. And so then what they do is they have 1/2 epsilon naught E squared times AD. What is the dimensions of A times D?
B.
It's volume, right? And so this is the energy density per this volume that gets us our potential energy.
So that's how it's described, okay.
Yes,
Because I
so
looked at it in class, I'm like, okay, how is this energy density if that relates to volume? But I totally forgot about that one.
so that makes it make sense. So that also wraps up the problems from your first exam. That was fun.
That's the word for it.
The units for this would be joule per meter cube or joule meter cube, right?
Wasn't fun at the time.
So
Because if you do it.
yes, it would have to be. Yeah. All right, I require the other
Did you
exam.
already shoot him the
The final,
practice?
I think I already sent it to you, like, go check.
Yes, you have. Doing dandy over there? Having a good time?
I'm living life.
Living life.
As long as I get all these notes down, I can transcribe them and send them to the group. I'm ready.
Transcribe them.
Transcribe.
I like to use the word transcribe.
Well, because like I can read them right now. I don't know if maybe anyone else could. So that's why it's like I'll do that later tonight and then send them to the group chat.
All right, so let's solve another problem. Wait, yes.
You like the main one, like the physics too?
Are you doing the
These are all multiple choice problems on this practice exam, Sammy.
did you do the
Wait, are all the?
It should be in 2 parts. You should have multiple
Yeah.
choice at the top and then a mix. of
The second, the mix is the bottom?
Yeah, it should be a
did
mix.
you open 2 out of 2 or just 2?
Maybe I
Or
lied.
just sample?
No, they're all multiple choice.
If
Right,
you-
'cause
you-
No, it's not. Number 20 is not.
Number 20 is not? All right. We'll do that one
Number
first.
10 is.
All right. Oh, well, number 20 is optics.
Oh,
You said there's gonna be no optics in your exam, right?
thought he said it
Hopefully not. He covered each bed. And like,
I mean, he did the same thing with particle drift too. Drift velocity was on like 4.
That's what I was saying. He might put drift velocity in there.
You showed us a graph of how drift velocity behaves and then skipped all 5 slides that talked about it and then put 4 problems on it on our test.
Useful.
going back to your notes.
Still wait.
That's been the whole semester with
Still wait.
it.
Yeah, I went and read it and made my own.
And so when people come in, I always ask you how.
Yeah.
Everyone's like, oh, I forgot.
That's pretty useful.
I'm so sorry.
Yeah, can I went to James and they
Honestly,
I know, right?
Yeah, bring my book with me.
That's the
you
one.
should walk up to his office, ask, are you Sean with the exam?
I think he already said no.
He said no.
I think he laughed it off.
All right.
Somebody asked
Well,
today.
in light of the fact
Yeah.
that he said that there's no optics, would you guys want to select specific problems from this exam to do so that we're not just, I mean, I can just start from number 1 of part 1 and just start
I
going.
mean, that works for me.
Yeah.
That works too. I mean,
We've still got a little bit of
You
time.
still got
We got an hour
Yeah,
and a half, so hour and 25 minutes.
Yeah, so I mean,
We
why
can-
not
we
just
can
start
have
from the
final
beginning
exam in
and
an
work?
hour and 5. Kind of things in fact.
Bold.
We can do the whole
You guys ever heard of speed running?
Yeah, we have to
How long
find
is
the.
it? Yeah, you think we get to the 3
hour
hour
exam?
exam? You think I can teach a 3 hour exam in an hour and 25 minutes?
Yes.
You could probably do it without it.
Yes, I can answer the exam.
Yeah,
I mean,
every other.
if you
multiple
just-
choice until you get to the ones we work out.
There are none that we work out.
There's no workout ones.
Yeah, there is. Did you send him the full thing? If you send him, example number 2 out of 2, that's all the ones we worked out. There's only ones that we worked out.
I have part 1 and part 2, and all of the questions except for the one on optics is multiple choice.
Yeah.
Is the
Yeah,
second
so
one
you
is
go
in
to-
the course document?
You go to sample examples on Blackboard.
Do you just want to email it to me? So he's
Yeah,
not
I'm gonna
searching
say
on
Oh,
it?
shit, yeah. I have your email.
Oh, sample exam 2 out of 2.
I mean, you are in my class, or
Yeah,
were, I
that's-
should say. Speaking of which, for those of people who are in my class, are all your grades updated? Did they-
Yes.
I got 100.
Yes, I really liked your last article.
Latex.
Boy.
I worked my ass off for that. Hey, leave me alone. I had to go back, because remember who fucked up so bad on both of our last 2? I had to go back and fix them both by myself, while I had to do the next one.
We're on Zoom.
They're
not trash.
Oh, yeah. They'll be alright, they know what they did. They know what they did. Hello, they know what they did.
I
hate you all.
Alright.
They know what happened, they know that.
Let me check my grade of that grade.
Your group's killing it. I don't think there's anything you have to worry about.
Well, I'm
You guys use LaTeX, so you guys have like 100 extra bonus points right now.
We use it like twice.
Yeah.
Even your group
What
is
you mean?
The problem is that like half of us wait until Thursday night to do it.
Actually,
It's just a pain.
Joshua,
It's a pain in the ass.
Joshua, can you check your grades right now to see if I updated your lab 7? Because,
Because, when I checked.
one of mine says
when I
needs
checked
grading.
last night, I was sitting at a 98.
But I think that's just.
For lab 7?
I know, at a 98 overall.
Oh, I don't even know your overall
Is
grades.
lab 7?
Lab,
Is the lab 7?
Mine's not.
my grades. The lab 7.
The hit cube.
Lab 7 for me is 110 out of 100.
Good, all right, that's because,
I didn't buy it, it
so
was free.
Francis has been, like, I've been trying to update it a bunch of times,
Too
and
loud.
he's had to email me like 10 times to try and
I
get it
broke
actually updated.
I broke the.
He just, he, for his class,
Like,
like,
that one
because
doesn't-
his lecturer is gonna listen to all of ours. Like, I'm pretty sure, all of us are Wigan, right?
That's just
Yeah.
switch.
Yeah.
So quick.
So like, I think he has a different
It doesn't
lecturer,
make
I don't
that much
know,
noise.
I don't
It
know.
does,
if
okay, look, it
um,
does if you like press it like that.
like,
You can
if
keep it in
so-
your hand.
I would tell him, in my personal opinion, just fuck
I
up,
used
get
one for a while,
110.
but it was too loud.
That
I just found it in my bag. I was like,
Yeah, you guys will be fun.
The only lab we don't have in
Is lab 10.
Lab 10.
Yeah, lab 10.
Which is the one that you guys have not turned in yet, so
Right,
there's no way for
other
me
than
to
that,
grade.
all of my lab grades are in, so.
Yeah,
I have all
mine.
mine.
You're up to date?
Mine says, mine says I didn't use when he's grading, but I didn't.
It probably means that I didn't click on the actual thing. Did I put a grade in?
It's a 90.
Yeah, I put a grade in, but I didn't actually, what's it called?
Saying it,
Click on your actual, because like I said, I can't read the Blackboard stuff. So like I have to like, half the time I have to email people, be like, can you send me your paper grades?
Oh.
Because I am terrible at technology, so.
Me too.
I love technology. That's like my best friend.
So you kind of have to be in our field.
I know, right? Yeah.
Okay.
Can't be going into.
Yeah, this is a good example of this.
Weren't you gonna major in physics for a while?
That was the first choice.
Did you guys like when I went through like the process in my head?
Yeah, I was gonna say,
Alright.
if you just, instead of like trying to teach us, if you just wanna work them out and we
In
talk
front of you
about.
guys?
Yeah.
Alright, that would
And
be
then
that, sure.
ask questions as we need. them.
Yeah, well, let's do that, and then we can keep ourselves moving a little bit.
If you get stuck, then we can help out.
Or vice
If
versa.
you just start everyone.
Yeah, we can help out. Collectively.
Our numbers, bro.
You guys got it.
Alright, so for the first problem, we have a wire. We know a potential difference between, alright, so we have a wire.
Are you talking about the 2017 version?
No, it's on sample exam.
We know our radius of our wire, so
2/2.
radius is equal to 2 millimeters.
Yes.
Thank you.
2 millimeters. Our current is equal to 2.5 amps. And our potential difference between the points of the wire that are 46 meters apart, so it's a very long wire. So this 46 meters, this marker is starting to die as well. Is equal to, what's the potential difference? Was it
3.7 volts.
3.7 volts. All right, so the first question asks, what's the electric field in the wire?
Oh, that's easy.
Yeah, delta V over
D.
delta D, right? So electric field is, this is how I would do it, delta V over delta D. We know delta V is 3.7 volts. Our distance is 46 meters.
It's like 9.
Answer.
0.09, roughly.
I don't care. The second problem is to find the. Oh, no, I this is as far as I like ever taken it on exams, so. No, I actually haven't put a numerical answer on anything in like years.
Really?
Yeah.
Is it all just like theory based?
Like our answer is like derive this. So like get to that.
Oh my God.
Stop at that point.
Yeah, that's partially nice, partially not nice.
True,
You
true.
don't have to worry about messing up the timeline.
And so the second part is to find the resistivity, which if we remember back to our lab was a rho is equal to R L over A, I think. Or is it R equals?
It's R equals rho L over
Okay, so this is the correct one.
A. Yes.
All right. So we can start from that. It just means I have to flip what I was doing. So that this implies that rho is equal to R A over L. We know Ohm's law is V equals IR, which implies that R is equal to V over I.
That's all for rho, right?
Yes. So then we need R first, though, because we know that we are not given the resistance of the wire, or the resistance in that
Ohm's
section.
law.
I just did. I'm on it. So rho is equal to V over I, A over L, which is all things we have. So this is going to equal 3.7 volts times our area, which is pi times 0.002 meters squared, divided by 2.5 amps times a length of 46 meters. That's going to equal our answer.
How come you just using the circular end of the center of the wire?
It's a straight long wire, but circular
Wire
wire.
comes out of it. Okay.
So it's you can think of it like we're looking onto a copper wire.
Okay.
So it has some face area, which is pi r squared with the radius.
And that's the one that's okay.
Yeah. And the length is how far this wire travels. It's the exact same as if you remember from our labs where we laid the wire down on that like black block and stuck a charge across it and moved it. We calculated how the resistivity changed as a function of the length, and we found that it was a constant because resistivity is a constant of the metal.
Wait, what?
Is that pi?
This is pi, yes.
Okay.
Pi actually sounds pretty good right now.
I could go to pecan pie.
Hello.
Pecan pie is so good.
I'm more of an apple kind of guy.
Oh, you're basic.
It's not bad.
He's basic.
Pecan pie is like, I'm not from the South, so when I came down to
Apple
the South and
pie.
had pecan pie, I was like, okay.
Apple pie and vanilla ice cream.
Right
man. Can't
Do
go
you
wrong.
guys know, they're the spirits flavored ice creams from Haagen-Dazs. They have like bourbon vanilla,
Mhm.
and like if you put some of that bourbon vanilla with some pecan pie, nice and warm, okay. Sir, making me hungry.
I'm getting hungry.
Yeah, I don't usually buy food on campus, but I did because I know I was staying late.
Yeah, I did not think my bar Well, not also that, but like. I
Does anybody here live off campus?
Yes.
Does anybody have no internet today? My internet was down all
I
morning.
mean, I've been here all day.
Yeah, here.
Because
I mean,
I didn't want to have to come in.
What
until
defines morning?
11, 12.
Oh, I was already out of the house by then, so I don't know.
There's a 0% chance I'm waking up before 11.
Who's your internet provider? If it's Cox, then probably.
Yeah, I fucking hate them.
So my family had Cox, and after a while, once noon hit, it was like noon almost every single day. Every computer in the house would lose internet.
It's
So
so bad.
they don't have enough room on their switchboards. So when a new connection gets made, you get knocked down one. And then eventually you get knocked off of their list and you have to reconnect and you get put back at the top.
That's crazy.
Because all of their stuff, all of like their entire infrastructure is stuck in the early 2000s. They've not updated at all.
So frustrating. Fortunately, what's nice is I do all my work like post 8 o'clock when nobody's on their fucking shit, so I don't have any problems.
Yeah.
But like this morning I woke up, I'm like, oh, I have to submit my homework. And I was like, I'm gonna have to drive to campus just to submit my homework. All right, so the next problem is 4 resistors are connected across an 8-volt DC battery as shown in this figure. So let's draw that.
Why do I feel like I asked you a problem about this?
You spent a lot of time talking to me about capacitor problems like this.
This is a resistor problem.
This is just a resist. This is just a
Simplifying the
I
circuit.
think this one was pretty simple to me. I don't know.
yeah. I don't think this one's going to be terribly tough, but I want to, having an example of resistors before you go into your finals is always useful.
Yes.
It's a resistor problem. There's going to be one on that exam. So
Yeah.
So it has to be.
This has to be.
yeah, we see number 2.
Oh, is this not number 2?
Oh, did I skip one?
Yeah.
Oh, shit, I'll go back. I'll go back.
Oh, this problem?
This-
I think I must have skipped one. You hit out?
Yeah, I got it out, so, yeah, good luck. Like I said, I'll transcribe what I can find, all that shit. But anyway, you all
Yep,
have
the
to
recording is over there.
He said all that shit.
All right. So, an 8-volt battery, 3 ohms, 9 ohms, 2 ohms, 4 ohms. And so what are we asked to find? The current through the 9 ohm resistor. All right, so this is a good problem to ask. So the first thing we need to do is we need to find the equivalent resistance of the circuit so we can find the current across the whole circuit.
396.
So this one's going to become 12. This one's going to become 6. Then we have REQ is equal to 1 over 6 plus 1 over 12. This is 2 over 12. This is 1 over 12. 3 over 12. Which is equal to 1 over 4. So the inverse of that is equal to 4. So the equivalent resistance is equal to 4. So we can rewrite our circuit like this. Four ohms, 8 volts, and we can calculate via Ohm's law the current through our whole circuit, which is V equals IR. We want to find I, so it's V over R equals I, so this is going to just be 2 amps across our whole circuit. But that's not what we're asked. We're just about asked how much current goes through the 9 ohm resistor.
Yes.
Yeah. So we have to think, how does current split based on resistors in series? I mean, in parallel. Because the first step we need to do is we need to find out how much current is going this way and how much current is going this way.
They add up together.
Yes, the current junction, right? The current here has to equal the current here. So
Like, if you're one more current be going up to
the top one.
Yeah.
Yes, you're correct because
So
there
for-
will be if there's current going up top.
I was gonna say it would be.
Yes, it's gonna be
It'd
2/3.
be 12 over 18 times the
Yeah.
times.
You're doing-
Times the current, yes,
Yeah.
yes. Because so the way to find out how much current is going through each path in parallel is to so it's like he said 12 or 18. What you do is you take your what's it called?
You take
so
the one
the
you
way-
want to find times the source.
So if you have we're just gonna draw a simple circuit to write the rule out nicely. So this is R1 and R2, okay? If you want to find out how much current is going through R1, you take R2 divided by R1 plus R2 times I total. And then for finding how much goes through R2, you do, so this is equal to current through R1. But then if you want to find out how much is going through current of R2, that's going to be R1 over R1 plus R2 times I total equals I R2. Right? So that's exactly like what you said. It's going to be 12 over 18 because 12 divided by 12 plus 6 is 18, right? So or 2/3 if we want to simplify it down. Yes, that's only a rule for parallel. We're gonna have to account for how much is going through series in a second, but if you remember from the lab, what happened with current in series? Yes, it's because current is conserved in series, so it's gonna be the same for both of them. So once we find this, we actually have our answer. But I'm sure that when you are turning this in, he'll be like, well, you told me it's through this 12 ohm resistor or some shit like that. And you just want to probably make a note when you're saying like it's the same because it's in series. So that he knows that you understand that current's conserved in series.
Yeah, he's like, I don't read the word.
He doesn't read your words if you put anything, so you just put like resistors.
That's a fucked up way to grade.
He just looks through your number.
That frustrates me.
And that was like 90% of my work was on my paper was his words explaining what I was doing.
As you've
But
clearly
the
said,
part that's funny is like he says in his
2/3
instructions,
times
please tell me how you got your answer.
Yeah, so 4/3 amps is what's going through.
The 3 and the 9.
Yes, the 3 and the 9. Wait, shoot, that's going through the top one then. Because
Oh, yeah. it
yeah,
would be
so
going to
we want the
top
one going through
yeah.
here, so we need 1/3.
Yeah, so you want 1/3. 1/3.
yeah.
So like.
So 2/3.
0.7.
Yes, so 2/3 of an amp are going through our 9 ohm resistor. Which, is that an answer that he asks for?
It's roughly. It says
0.7, yeah.
So you just circle that.
Yeah. It's kind of annoying that he also gave you 0.5.
Well, it's
0.6.
0.6666666.
It's closer to 0.7, but it's still frustrating. Yes, man. Let's figure out this light bulb problem. Oh wait, shit! It's a conceptual problem. Do you have the answer key?
Yeah, it's on the other.
You should tell me if I'm right then.
Do we have the answer key?
It's
You believe in me?
final is the answer.
If I think.
Figure so then number 2, I think number 2 is more of a conceptual problem rather than an actual derivation problem. It's like you have to just think about what happens with these light bulbs.
There is optics and everything up to and including electromagnetic waves.
You're lying.
Electromagnetic waves.
Well, yeah, I think that's.
Electromagnetic waves isn't really optics as much as like Snell's. Like I don't think Snell's law will be on your exam.
I don't know.
Oh,
I've
no.
You better have. You showed up to my
I was
lab.
gonna say,
Yeah.
one of the labs.
I mean, like, I don't know that I could do it.
And almost every single one of y'all got the plot wrong for finding the coefficient of refraction. So-
Absolutely, we did.
I did not.
Wait, were you the group that had a negative coefficient of refraction?
No.
Okay, one group had like a -10,
Nice.
and I was like, that doesn't even make sense.
A negative refraction.
I was like, okay, but like they did the analysis, right? I didn't take all points.
No, we only had.
No, yours was actually pretty. You had like 1.4 was your index of refraction, which was close to what it was supposed to be. A lot of people had the axes flipped, such that they were getting like 0.6 or something like that, and so I was like very close. But anyway, besides the point. For number 2, we have a figure showing 3 identical light bulbs. So obviously, if they're 3 identical light bulbs, assuming there's no heat going through them, because as we've learned in our lab, they're non-ohmic resistors. But when there's no heat going on there, they're equivalent resistors. That's essentially what we can think of these light bulbs as. And if they're identical light bulbs, even though they're non-ohmic, they'll continue to have the same resistance at all times. So you can just treat it as R, right?
Mm-hmm.
And so we have this circuit on where the 3rd light bulb is off. It's not on. So we only have 2 light bulbs powered. And as such, we have some brightness in light bulb 1 and light bulb 2. When we connect light bulb 3, what happens to the brightness of light bulb 1? That's what it asks. You guys know, right?
I think it is.
Nothing, right? Because it's in series with the rest
I
of
was
the
gonna,
system.
I
Yeah.
was gonna ask if it was in sequence. or-
Yeah. 2 would dim. 2 would dim because
Parallel, right?
because it's splitting some of its current with
Yeah.
light bulb 3. But light bulb 1 is in series with this quote unquote equivalent light bulb that's shared by 3 and 2. And so 1 has no effect. Cool, we can move on to number 4.
Here I got right on the last.
A uniform magnetic field of 0.8 Tesla in the negative z direction is present in a region of space as shown in the figure. A uniform electric field is also present and set at 76,000 volts per meter in the y direction. So strengthy magnetic or electric field. Electron is projected with initial velocity of v0 in some x direction. The y component of the initial force. Oh, we want to find the y. So he's actually asking us to find the y component of the force, which is kind of a strange way of asking. He said the y component of the initial force of the electron is closest to which of the following quantities. Which this is a multiple choice question, but this is a really good question to do. So we're gonna do it.
F equals E cross B, right?
So F is going to be equal to E plus Q V cross B. Because we're going to be using the Lorentz force. That's what we're going to do.
Use Lorentz and get Coulomb force as well. So
Sorry?
don't you use Lorentz and Coulomb force?
Technically, yes.
And you add them together, right?
That's what the Lorentz force is. So you're thinking Lorentz magnetic force is just the B, or the FB is equal to QV cross B, right? Technically, the Lorentz force is defined as the entire thing.
I didn't know that.
You learn something new every day, right? And so, as such, you can write down this nice equation that I just said, that the force is equal to Q times the quantity of E plus B cross B. These are all vectors. And obviously, as you guys might be kind of getting alluded to, he asked for our component of the force in the complete y direction, but all of our components are going to be in the y direction again, because our electric field is given in the y direction, and V cross B is in the x and z direction, so that our cross product automatically has to be in either the y or negative y.
Yeah.
So as such, he's basically just asking us to find the magnitude of the force, just phrased strangely. So don't be tricked.
I'm very tricked.
You feel tricked?
I'm very tricked.
So let's perform our cross products. How do you guys do your cross products?
A cross product calculator.
Do you guys do the determinant method? The determinant method, because the nice way to do cross products, as just an aside for those of you who are in advanced math or go into physics, you will see cross products written like this. So it's gonna be is it over I of
that's what they.
or no, it's VJBK. Some of that. And so that's how you represent cross products in a fancy way.
Yeah, I still do the what's it, Strozak method. We just go 2 columns.
Yeah, so that's what I'm gonna.
That's determinant.
I'm gonna use the determinant method because it's for a simple cross product like this, it's nice to keep track of things without having to go into some fancy definition using the Levi-Civita symbol. So, but just for those of you who might see this, it's related. Cool. It's for the culture, if you will. I had a professor that the longest time he would always do the problem the way that we need to know, and then he'd do it some fancy way in like 5 minutes, and he'd be like, "You guys don't need to know this. It's just for the culture." And so,
Why?
I don't know. I enjoyed it. I thought it was cool. So
Yeah, that's only
this is the cross product method that I was taught in Calc 2 or Calc 1, wherever you learn cross products. And so you put your first vector, which is our v, in the first component here, and our v is equal to, I'm just going to call it v0 x hat, right? Because I don't feel like writing numbers, 0 in these terms. And our, what's it called? Our z field is, our actual z field is coming out of the page, and our magnetic field is going into the page. So we have a negative v0 in the z hat. So it's negative v0, 0, 0. That's the cross product that we're doing, right? That look right to everybody? Everybody agree with me? Cool, wonderful, great. So you compute this cross product. Obviously, the only term that's going to survive is the y hat component on the first, the positive term. So what we're going to get is so this becomes negative j hat times v0 times negative v0 minus 0, something like that. So we get negative negative. So you get v0 v0 in the j hat direction. Does everyone agree with that cross product result? Cool.
This is really useful to go into the next part. So you can do these on the calculator too.
Yeah, if you can do those on the calculator, all power to you. I cannot.
I've had this calculator for this whole semester.
And so now we can go ahead and just, plug in. We have Q, we have E, right? So E is equal to some E naught in the y hat direction plus our V0 in the j hat direction. And so we can see that our force in the j hat direction is just the magnitude here. So it's going to be Q, E, E naught plus V0 plus V, it's not plus, it's times V naught. It's just this. Another marker this time.
RIP marker. We're just eating up your markers.
This whiteboard is really bad on them, but I don't know what it is. I think it's because it's like this plastic material, like whatever, this glass. It's not as nice as the regular whiteboards. Fortunately, I have about 400,000 blue markers. So.
Also, there's like a huge box in the upstairs
It's true, but I also steal all the blues. So.
Is blue just your color?
I only write in blue. It's just like
Weird.
a little.
Does that include your regular pens?
No, I write black pen, but for markers on the whiteboard, it has to be blue. I have a box at home. I think it's a box of 500 blue expo markers.
Oh yeah.
Because I have a whiteboard at home that is just covered in blue marker. So.
Oh, yeah, I guess you could take that vote. But I just remember the front to 7C2, and you just hit very full. And then it's all.
Words of the game.
Has to be blue.
So does that make sense to everybody where we got the magnitude of our force field here?
Yep.
So you do a cross product and then vector addition and then multiply it and then find the.
And then find the magnitude, which is all we're asked for. So just take the coefficient out front. Because he asked for the magnitude in the y direction. It turns out that it's all in the y direction. So it's just the magnitude. And by the way, the E0, V0, and V0 are just the numbers that he gives.
Yeah.
I like, as you guys have noticed, I don't use them. So number 5 is a multiple choice problem. It's exactly the same thing. Now we don't have an electric field. So now we're going to be using what you had previously referred to as the Lorentz force, but it's really the magnetic force, which is, FB. So it's just do that or do that for this problem. So I'm not going to do that one. I feel like that would be redundant and a waste of time. So I trust y'all.
But just Q times V cross B.
Yeah, the Lorentz force for that one.
Yeah, so the Lorentz force in full is that thing that I wrote up there. Like it's Q E plus V cross B. The magnetic force is just Q V cross B, and the Coulomb force is QE, right? So
He just described the Lorentz force as QV cross B.
that's just the way I was taught. So
That's definitely.
I mean, it makes sense because if
Right, that's
it
what
just
I'm
says
saying.
1,
That's
0.
really better.
yeah, so I don't know. I can only teach you what I know.
The funny part about like Tim's class and him talking about the he was telling us to do the like the little review, like a little peer review on his class, on his course. I was like,
You don't want that from
You
us.
don't want that. You
Yeah.
don't want that, buddy.
Did you write a review for your lab, Professor?
I never got.
I think I
I don't think we ever got an option for.
I
mean,
mean,
yeah,
you like always across the board.
They don't,
So don't worry about, it.
Perfect
You always
teaching
across
style.
the
they
board.
don't give us the
Right.
opportunity for a
Literally
lab.
taught me
I am
more
not
about
on
like
my
texting my
professor.
professor.
There you go.
You should be.
That should be, thank
Should
you.
be.
All right, so an alpha particle is moving.
All right,
at-
celebrate my
Oh,
Have
okay.
you seen his Rate My Professor page?
Oh, it's bad.
It's bad.
Wink, wink,
Wait.
yeah.
You wanna look up somebody really bad? There's one professor that I have named Politsky, who has like a straight zero. Just like you go to his class and you just, like, I really like him as a person. If you go to his office hours, he's incredibly good at helping you, but his actual in-class lectures are beyond useless to help anybody with anything. You go to class and you literally just watch him write stuff on the board and speak, and you're like, I learned nothing. And then you have to go to his office hours, ask him a question, you're like, oh, that's what you meant. But like, you know,
Now it makes sense.
it just,
Now it's
like, at what point during the semester do you just stop going to class and just go to office hours instead? Like,
Right.
Yeah, I only chose wagons to keep my Fridays free.
He was on Wednesday.
Yeah, he was the only one I could take.
He's
He
the
had
only
to
one I
go
could take.
to a one class.
I
Or
had
all
choice.
ones.
all right, so an alpha particle is moving at the speed of some speed direction perpendicular to a uniform magnetic field of strength. Some strength. The charge is some charge, and its mass is some mass. This problem is actually a really useful problem, and it leads me to we'll do this problem in full, and then I'll make a discussion, a little point that there's a neat problem that I was asked on my final exam when I took this class back however long ago that was, about what the velocity had to be in order going through an electric field magnetic field combination such that it traveled in a straight line. And so if you had an electric field going this way and a magnetic field going like this way or something like this, like how do you shoot it? Like what's the speed? And it was a neat problem and something for you guys to consider. But let's do this problem in full because we have just a particle entering a magnetic field that's perpendicular to its direction. So as such, we're going to be nice, kind to ourselves, and we're going to operate completely in two-dimensional space and pretend that the third dimension doesn't exist. And in doing so, we can simplify our problem down quite a bit. I'm going to erase this. Sorry, I like clean whiteboards.
I do like simplification.
And so if we allow our magnetic field to be in the y direction, so this is y, we'll put the magnetic field along the y, so y hat, and this is our x direction, and we allow our particle to be traveling in the x direction, right? So here's our b0 x hat, right? We want to find the magnitude of the radius that this particle curves, because obviously when it hits, it's a cross product, right? So the force is going to be felt in some external direction, and we're going to be finding out how much it curves based due to that force. And so the neat trick about this problem is we're going to be treating this as something you guys might remember from when you took physics 1, which is the car going around a curve problem. The centrifugal force, that's what we're going to be using, right? And so if you recall, we'll do a quick aside, that this is equal to ma, right? That's just Newton's second law. But the acceleration in a centrifugal system is v squared over r, right? And so as such, our centrifugal force is equal to mv squared over r. This r is the r that we want, right? And so interestingly enough, as it's traveling through this system, we can set up a equivalent free body diagram that I'm going to skip over, and we're going to find out that the centrifugal force is equal to the magnetic force, right? And so that's the problem statement. That's really all we need. We can go right ahead, start plugging things in. We get mv squared over r is equal to q v cross b.
Is this the case for this, just this question, or is that like conceptually?
That's conceptual. So when you have a particle in a magnetic field and you want to know how far the radius is, as long as, I mean, actually, you can actually do this for any, as long as the magnetic field and the particle are not in the same direction, this will work. And the only reason that that won't work is because like I cross I is equal to 0, right? Because they're vectors in the same direction. You have to have some difference in angle for the cross product to have any physical meaning.
So they have to be going in different directions, or
They can be going like we could have, you can have a like a V0 here and a V0 this way. Your cross product, you remember the definition of cross product. So V cross B is also equal to V sine theta, the magnitude. And if you do this cross product, you'll get some combination of vectors with some strength that corresponds to the sine of the angle. The only reason that we, in most of the problems that you'll see, don't run into this issue is because we have our vectors perpendicular, so that it's nice and our math results in the a vector in one direction. But I mean, if you guys wanted, we can do a problem like this so you have exposure to it. But if you don't think he's going to ask it and you are kind of comfortable with how cross products are working, then I don't think it'd be worth our time. Because I mean, you can like, it's just like if you, as long as you know the directions of your V and V, you can perform the cross product. As long as they're not in the same exact direction, you'll get some resulting vector. That's all you need.
okay.
So just do the cross product. Like when all else fails, just do the math. Right? So let's do our cross product here. I, J, K. For those of you who can do cross products in your head, I'm very sorry, but I'm also very jealous. So just bear with me. So this is V0, 0, 0, 0, V0, 0, right? So obviously the only term that's going to be contributed is from the k hat direction. So it's k hat V0B minus 0. So it's V0, V0, k hat. So if you remember our right hand rule, that means that it's coming out of the board, right? So the force is coming, we'll write it as I, that's the force, right? It's equal to, it's equal to V plus B. So we can go ahead, we can plug that in. We have mv squared over r is equal to q v. I'm just going to call this a v and v now, just because this v on the other side is the same v, so I want to do some cancellation. vb, and then our resulting thing is in ek hat direction. But we only care about the radius, so it doesn't really matter what direction it is. We just care about the magnitude. You can drop the v, move the r over, divide by the qb. So mv divided by qb is equal to our radius. Voila. It's a neat problem, and that's definitely the type of problem where he could throw something at you with just not perpendicular fields, and that's a very straightforward type of problem that you can ask on a final. So I would make sure you understand this one.
I guess the main thing here is understanding the cross product.
Yes, that is, when you have a particle in a magnetic field, it's just the cross product, and you can always just perform the cross product and call it a day. If you're coming back, you will need to stop so I don't have to get up. And so the second part is just asking how long does an alpha particle take to make one complete revolution around this path? Do you guys remember how to do this one?
Just angular velocity over the circumference.
Yes. So we have our radius, so we can find our angular velocity. What's it called? Which is equal to radians over time. We want to know. All right, now, cool. Am I losing a variable? How would the meters cancel out?
Let's ask the internet. It's the best way to do these things.
The angular frequency
So
is V over R. That's really.
you said angular frequency is V over R.
That's related to QB over M.
Yeah, so
If you divide and flip it, then that's how you get it.
yeah, so it'd be the inverse.
Yeah, so take that 5 by B and inverse it, that's your angular frequency.
Which we want the period, right, which is 1 over the frequency. 1 over the frequency times 2 pi, or is it just 2 pi? So
It's
2 pi f, right? So period is equal to 2 pi f, right? And you just said to me that frequency is equal to V over R.
The angular frequency is.
So this is omega.
Yeah, omega equals V over R, and then
That's
omega
true.
equals 2 pi f. Now,
Yes, and then
you solve from frequency is 1 over the period.
very well done. You should teach.
I mean, Sean's is really helpful.
So is this going to be V over 2 pi R equals F? So what we need is the period is going to be equal to 2 pi R divided by V, which is R is equal to this. So we get 2 pi M divided by QB is equal to the period. Well done. Thank you. The units check out with that. That makes sense.
Alright, I know this could be a dumb question. Do you know how to use GrabHub? Apparently, because apparently GrabHub does not work for me.
Grubhub is great, but I don't know how to use it on campus.
No, it's not.
That's great, you have to add campus dining to your account.
Oh, really?
I can use my own plate everywhere.
No, I'm thinking like when I like joined like.
I have private
It was only
I
like
have this in my bag forever, I haven't taken it out.
Cause GrabHub is like super annoying. Like if I try to GrabHub something, it'll say select payment and I'll say like, oh yeah, I'm doing a meal exchange on my ODU card. And they would just be like, they would usually accept it, because sometimes it doesn't, it just says like select payment, when it usually automatically just says meal exchange. I mean, and even if I do try to select it, it's grayed out, so I can't select it, so I'm like, this is gay as hell. So annoying.
Magnetic field just looking at P. Very interesting way to use the force. Is there any more full open? Yeah. Can we skip to number 9 since it's a open problem, not a multiple choice problem?
Yeah, that's fine.
Bar moves along. With the bars 1.6 meters and the uniform magnetic field is 2.0. As shown, was the applied force required to move the bar to the right with constant speed of 6 meters per second. All right. So we need to find the Lorentz force in order to get a certain result. Is that what I'm reading? No. This is
This is I've done this problem before with a different student in my office hours. You need fuck. You guys have this equation? Oh, here, let me start from the beginning. Because if you don't, this might be something you guys will want to use. The electric field, correctly, is equal to BLB. And then once you have the electric field for this case, you can find the current rather quickly, if I remember correctly. Scroll. Yeah. I should go ahead and I should derive that in full. How did we do that last time?
What does L do in this?
Like,
Yeah, and E is not the electric field. This is induced potential. I just have my notation not that great right now. I'm gonna read the goal. It's E. So you read it nicely. The way you do this problem, I'll write it out real quick, and then this is what the notation you guys might have seen is. The ILV? What is the force? It's ILV. Or
Which force?
it's the Lorentz force, but in terms of the current. It's no. It's ILV. It has to be. Yeah, it's this one. So you have normally you have Q equals V cross V, but you can also have that one. Same thing. This is the one we're using, but where these are perpendicular, so it's the ILV. Which then once you have all this, you can just plug in and get the answer, which is what we need, but give me a moment, you guys don't mind. See if I can find the yeah, okay, so that's correct. Which is fine. And then obviously power dissipated is just P equals I squared R, right? And we're given a resistor, so take your I, square it, multiply by R. When in doubt, ask Google. Motional EMF, Lumen learning. Oh, okay. So yeah, this is a Faraday's law extension. So let's do it from the beginning without having some, prior confirmation bias. So you guys are used to seeing that Faraday's law is equal to, or just EMF is equal to n negative n d phi dt, right? That's the traditional way of seeing Faraday's law. In this case, we have a solenoid with one turn reality, it's just one loop around. So n's equal to 1. We can drop that, which is kind of nice. We can also recognize that for the sake of simplicity, we can have a magnetic flux going in the negative direction, drop the negative sign. So we can reduce this equation quite quickly to just equal to this. Right? And this is all great until we have to actually calculate anything, which doesn't help us much over here. But if you remember that sigma, or phi, I should say, is BA, right? Well, it's really an integral, but when they're, perfectly collinear, it works out nicely. And so this equation, when, reduced into its simplest form, is really just, I'm missing something. I'm missing. No, we're good. Yeah, we're fine. I'm not missing anything. This is delta A. That's what it is. There we go. Sorry, long day, guys. For now.
Are those deltas?
These are dells for
I was
partial
gonna say or
derivatives.
del.
Um,
Okay, just making sure.
As I might do, you can also treat this as B delta A over delta T. It's fine. What I'm going to end up getting to here in a second is that for this loop, we have a length and we also have an infinitesimal x that we're going across, right? That we would traditionally integrate with. So you can reduce this to a length times a delta x over a delta t, or a BL dx dt. What is dx dt? Velocity, which is how we get at this BLV equation that we were using. And so once you have this is equal to your EMF, you can take this up here, solve for the current, and then use this equation to get your answer, which is just the nice condensed form of the cross products where the sine of the angle is equal to 1. So that makes sense. I do it justice in the end. All right. That's something. I think there's a second part to this problem. And then yes, so it also asks at what rate is energy dissipated in the 4 ohm resistor. Energy dissipated is equal to power lost. Power lost is equal to I squared R, as I said. So we can treat this as just U is equal to power is equal to I squared R. We know I is equal to BLV squared divided by R squared times R. Cancel one of these out, and you're left with BLV squared over R is equal to your potential loss. So I think that's rather useful for that. Ah. Oh, we have to include those. Oh, that's not fun. Will those contribute?
Oh, and superposition, does that work? Can I use that? The answer would be straight wire, circle. Superman. Just add 3 up, call it a day. Yep, so straight wire. Yeah, okay. Oh, shit, I need to get to that result. All right, do you guys know off the top of your head, like, do you have it for your exam? The magnetic field due to a loop and the magnetic field due to a straight wire? You do know those?
I'm not off the top of my head, but I definitely have it in my notes.
Okay, all right, so with that in mind, this problem is really straightforward. You just solve for the magnetic field due to a straight wire and add it to the solve for the magnetic field due to the circle, which makes it really, really easy. If you had to derive the expressions for, like, say, like from the units of art law, derive the expressions for the straight wire and for a loop, that would take me more time to do. But if you guys are familiar or at least have them, we can run from that so we can get the problem done, you know, before people start showing up to learn labs and I teach for another 2 hours and run my voice dry. What time do y'all get to campus, out of curiosity? Like on average here?
All my classes start at 11.
Okay.
9 or 11.
I generally leave the house at like 8:15.
How are you not like burnt out by now?
I am.
Oh, okay. I would just want to go home. Like.
I do.
All right, so the magnetic field due to a straight wire, just to keep your interest for one more problem. All right, we'll hang
I was
out
actually
after
going
this.
to ask if you could do an inductance problem.
We'll do that one. We'll do this, then we'll do that, and then we'll call it cool. So magnetic field due to a straight wire. We'll call this straight.
This is number 10.
Yeah, it's just equal to mu naught I over 2a, I think. Oh no, it's fuck. It's 2 pi r off the radius or off of the line. So if you have a current in a wire, the magnetic field at a point r away is equal to, well, as you guys know, if you put your thumb in the direction it wraps around the wire. So in reality, at this point, our magnetic field is into the page, and over here it's coming out of this, right? So that's what we have from that wire. And so we have all of those values pretty nicely wrapped up for us. The only thing that I want to be careful about is I don't need to be careful about that at all, do I? No, I don't, because it's okay, doesn't matter. We want to know what the magnetic field is at some point. There's a loop here too, right? So our r off of the distance is equal to the radius of the sphere or of the circle, right? So this is just equal to mu naught I over 2 pi, and I'm noticing I'm writing this as I'm writing r because I want to make sure that there's the radius of the circle, right, of the loop, right? And so we hold this value, hold on to it, keep it for now. And so now we just need to find the magnetic field due to the loop, which magnetic field due to the loop is equal to, it's mu naught I over 2a, I think. That sounds, or 2 area.
Yeah, that seems right.
But does that sound familiar to you guys? Wonderful. So our area is equal to pi r squared. And so this is really equal to mu naught I over 2 pi r squared, right? Make sure I'm correct.
No, it is over 2r. Whoever said that was right. It's just over 2 times the radius. So over 2r, so over 2r. And so the correct answer for the magnetic field at that point is equal to BS plus BL. And so you can add the, or you can pull out that, and you basically get mu naught I over 2r times 1 plus 1 over pi. Did I do that right? I think I did that right. Yeah. Oh, shoot. That's not fully correct. It's ignore me completely. I was just wrong. The B total is equal, it's combination of vectors because they're vectors. You have to do
Oh, yeah.
addition of vectors. BS squared plus BL squared. So that's how to solve this problem.
For this, for the magnetic field or the straight line,
Mhm.
the little r denotes the radius of the line, right? Or is it
The little r denotes the radius off of the
from there?
from the wire. Yes, that one I know. I know the magnetic field due to a straight wire. So it is. As the internet has told me, this is mu naught I over 2r. But I assume you guys can just know that if you need to. You can derive it from bias of art. I don't want to.
So how come you just can't use the magnetic field of circular loop here to find out the origin?
You do for this one.
Yeah, but is that the only one you, because you use that at the center, it's the square root of each of the squares.
Yeah, so the loop is this one right here. And so you need to add the result of the loop with the result of the straight wire.
So you have to do both of them?
Yeah, because they're both contributing.
Yeah,
If it
it's
was,
a total magnetic.
yeah, so
field.
if it just wanted the magnetic field due to the loop, it would just be that part right there, and then you'd call it a day and be happy with it. But you're not, you have to add the two together. It's what's called
And now
linear
it's
superposition, so. Is I think that's justifiable response. And before we head out, you wanted to do,
If there, I've not looked at it actually, if there's an inductance problem.
I will do my best to try and find one before my computer does.
I have some.
You have an inductance problem? All right, let's see it. No, seriously, if you have one.
Let me look for it real quick. I don't know which one you want to choose, but
See if nice. Oh, paperback, gross.
So these are the example ones that it goes through over the whole chapter in this section. And then these are ones that he actually derived. Where is that?
Oh, okay. That might be useful.
Inductance starts here. Just about here.
Yeah, let me see if I can find a problem for you. Do you mind?
Yeah, you can get those through.
Let's see what it has. All right. I feel like a lot of the problems that are here are very,
so you just using the only law.
it's like a plug and chug, but we can do one. I think that might be useful just to get some exposure to it if that's cool. with you.
You might have like more in depth in the back after like a whole chapter review. But I don't know.
I think what might be the best is if, as a group, even though the solutions are here and everything, we run through together the self-inductance of a toroid with n turns of square cross-sectional area A by A and inner radius R. If that is acceptable. This is what really all the inductance calculation wise is, it's a glorified way. You basically have to find the magnetic flux and divide by I. That's all you have to do. Every single time it says to find the self-inductance, it really just means to find the flux and then divide by I. The difficult part of the problem arises from a lot of times the integral that comes about getting the magnetic flux isn't always kind, which I think this is a good example of that being the case. And so as such, recall the magnetic inductance is equal to N sigma, right? So sigma over T, just N sigma. Sigma over I, N sigma over I. Right, that's the correct equation. I have that.
Sigma or
Phi is capital Phi. I just for some reason think it's sigma. That's what a full day of physics will do to you. Start being unable to read. Oh look, you know how we just did the problem with epsilon equals BLV? Equation 28.3 in your book.
I was able to tell you.
Great. Right, so they actually, in your book, they include N as part of the magnetic flux. I consider the magnetic flux just to be the integral of B dot dA. But your textbook, just for reference, seems to consider it equal to N times the integral B dot dA. As long as you have this in your numerator, you're fine. That's all that the real takeaway needs to be. So first things first, we need to find the magnetic field of a toroid, which is easy enough. We can treat it like a solenoid. And so you remember the magnetic field of a solenoid?
It's on my note sheet.
No, I'm looking at my book.
Oh, that's fair. I am looking at you. You have an excuse. Anyone else magnetic field of solenoid?
I can draw it for you.
Oh, wait, is it number?
Yeah, it does matter.
Number turns times mu naught I or something.
Yeah, mu naught I divided by
The radius between the center.
and
The area covered.
oh, so close. It's divided by 2 pi r. So it's equal to mu naught Ni over 2 pi r. You were very, very close. It's very impressive. I would not have remembered that.
I'm just
swirling
swirling it. It's like there's some area, but I don't know, I lost it.
It was close. It was a good attempt. I'll give it to you. It counts.
Mu naught
So that's a capital I. This is
Well, I was thinking A, but 2 pi r is the derivative of A.
very close. So you want to write it as this? You want to mu naught N I over dA of A. Yeah, I don't want to write like that either.
I mean, it would be dr.
Well, so when I say dA in that notation, just means to take derivatives that are whatever we need to. And so as such, we just now need to find dA. So what is dA in this case?
The radius, right?
Yeah. So it's going to be, but
Pi r squared.
well, I mean, once you do the integral, it can be pi r squared. This is the dA. So what essentially what I'm asking you is what's your Jacobian for your integral?
Yeah.
So when you guys go from what's it called? When you go from Cartesian to cylindrical coordinates, you add an r squared sine theta,
Yeah.
right? And then your dv is no longer dx dy dz, it's dr d theta d phi,
Yeah.
right? This is your Jacobian.
I've never heard
I
of
didn't
it.
know that's what it was called.
That was sci-fi. It is for you because you're a calc student and you're weird and you define your angles backwards. For those of you who don't reference what he's referring to,
It's sine phi.
yeah, because they have the polar angle as
Yeah.
phi and that's theta, so.
Yep.
That's how I learned it. Can't change it.
But no, so this is just gonna equal,
This is true.
the radius, so you can think of it as RBR, right? Or if we wanted to call the radius of our cylinder, and they do in your book a different variable, they call it lowercase a, whatever the actual radius of your
Like one turn.
of one turn is, throw it in, right? I'm gonna stick with this notation R. Actually, no, since it's a cylinder, I'm gonna switch to S. It's just nice convention. And so as such, we can just plug this on in. The dot product, they're in the same direction, they have to be, right? So this is just equal to, I'm gonna use my notation, not the one up here. Phi is equal to the integral of mu naught n, or in this case, over 2 pi r s dr, right? And they're all correct. Yes, because this r depends on where we are within inside it, right? And this s is only at the length, right? So it doesn't depend on as we go out. And so we can perform this integral and we're going to get some natural log. We need to be careful of our bounds, don't we? Shit. Where are we going to go from? We're going to go from, we go to 0 to a, that work? Yeah. Does it give us bounds? It should. Oh, okay, so it actually, no, so it gives us, for reference, a toroid is a very thick solenoid. So it's this radius they give us as R, right? And this radius they give us as R plus A. So in reality, I should have used A here rather than S, because this only depends on the distance of this. That's a toroid. It's crazy. I brought that in just for you.
Awesome.
Okay, so then our integral, this has to stay A then, because that is the distance of the actual thickness for the toroid. And we're gonna just go from R to R plus A, right? Yeah. Of mu naught in over 2 pi A up here, and then dr over R. It's going to result in some, I'm just going to call it gamma, which is just all this constant up front. I don't feel like writing it anymore. Times the natural log of beta, which is whatever the balance turns out to be, right? And this is equal to our phi. And then in order to get our L, we just multiply by n, which is to tell us how many turns it has. With n turns. So you just leave it there, times gamma ln of beta, which is just the term in, divided by I, and that's your answer. And so, like I said, these problems are very plug and chug. You just need to find the magnetic flux each time. It's really just how good are you at doing that integral.
One of the good news is that he referenced that post a lot in class.
Oh, really?
He's like, if you use this book, you can figure out my test.
That's probably a good example to have for an inductance-based problem. But I should probably stop teaching before I burn myself out before I can teach for another 2 hours. So hopefully that was actually helpful.
Thank you for taking 3 hours out of your day for us.
Oh, it's my pleasure.
See, when he says actually quite the opposite.
I like